So let's look at one or two scenarios. So let's say in scenario A, we have non-sealing fault plains and surrounding non-net materials, in this case shales, with poor sealing potential. So the assumptions here is that we have an early migration of hydrocarbon into the trap, in that basin, in that area. The faults are non-sealing, the shales are poor. Okay, I already mentioned that. So if you look at the top right, the figure on the top right, you see, a working system at time T2, a working trapping configuration at time T2. So let's imagine now that at time T3, we have some kind of, shortening in that area. And what you now see is that what you have on the hanging wall, the strata on the hanging wall has moved up, relative to the item on the footwall. And what that has created is you now have, remember we have a non-sealing fault. We now have sand on sand juxtaposition. So we have a leak. That's one. Okay, I'm back to scenario A. Okay, so we have a leak. That's one. And if you keep in mind that it says that the shales have poor sealing potential, that means even if we had anything in place, through time, things are going to go through those, those cracks, because why? The overburden shale has a very low capillary entry pressure. In other words, not the best seal to keep things in place in this trapping system. So through time, you see the gas, starting from the gas, because they have higher capillary energy, they're going to go through first, followed by the oil, and eventually you're going to have a total leak out of everything, and your trap is empty. So the outcome is that oil and gas, you don't have any of them, and that's all because of what we've seen: poor sealing around both lateral and vertical and overburden seal, and also poor non-sealing fault plane. So let's look at the scenario B that's got non-sealing fault planes, but shales with good sealing potential. Okay, so at time T2, we have this working system. It's completely charged from all directions. Let's assume again that the same compressional systems, maybe some kind of stress regimes in that basin causes some shortening, and you have the hanging wall move up relative to the footwall on the fault plane. Again, remember here we have non-sealing fault plane, so things are going to be leaking through to the other side. But in this very case, we have shales with good sealing potential, right? So we're going to have hydrocarbon, remaining on the hanging wall hanging wall of this system. But on the footwall, because the fault plane is non-sealing, whatever you have on the footwall is going to find its way out. So if I'm putting a well on this hanging wall, I'm going to, success story. But if I put it on the footwall, it's not going to work. And that is because of everything that we're seeing, because the configuration is not favorable for trapping or keeping hydrocarbon on the footwall. So if we imagine another scenario where we have non-sealing fault planes, I guess this is this is different from the previous one because it's non-sealing, and the shales also have good sealing potential. I mean, that works for us because even with the crustal or shortening in that area, we still have hydrocarbon trapped on both sides. But then here, the difference is this. If you look at the elevation, depending on the sealing capacity of the overburden shale or the gas entry pressure or the oil entry pressure, what we see is that we have a thin column of gas on the hanging wall with a very good column of oil, thick column of oil on the hanging wall. But on the footwall, because of the elevation, if you look at, let's say we have a regional gas oil contact in that basin, or we cannot hold gas beyond a certain limit in this area. What that means is that if I'm putting a well on the hanging wall, I'm going to find both oil and gas. If I'm putting the same another well on the footwall, I'm going to find just oil. And that's because of everything that we've talked about, which is the fault plane being non-saline and the shales being of good, the regional seals in this area. So this is the last slide I have. I think I probably raced through this too quickly, I guess. I'm not sure. But just concluding thought tells us that strata may become deformed, and when they get deformed, they create simple or complex traps, depending on the tectonic history of the basin. And we did say that knowledge of regional, technostratigraphic history is key, because it helps us, understand, or kind of early on figure out what to expect, even before doing detailed work in any basin. If I know that this basin, this is what is known about this area in terms of the tectonic strat history, I already have an idea of what to expect, and I can also, in the genetic sense, know where the different trap styles will be. In terms of, if you think of it in terms of structural domains, I know where to find traps that are very big or traps that are very small. For example, if you think of the trusted anticline plays and the stubborn conformity plays, you know areas where to find them. And you know that each of these trap styles have their inherent risk, for each of them. So it helps you figure out things ahead of time, even before doing detailed evaluation. So another takeaway from this short one is that the timing of the initial creation of fault or fold is key in trap analysis, because it helps us to know when or whether a trap has been created or breached and when that happened, of course, and then additional insights of hydrocarbon presence. By that I mean, if I know if this is a basin that was charged at a particular time, right? If I know that trap was formed or breached or so, it helps me figure out, okay, by this time, do I even have hydrocarbon? Do I still have a working system or not? So timing is very key in this whole analysis. And another thing we try to say is that polyphase deformation is one element that has direct impact on our trap integrity and our chance of finding any or specific type of fluid, because you may have an original working system at a particular time, but through time that trap may either become amplified in its quality or become degraded due to multiple phases of deformation that may have happened much later. So that's one very important message. So sealing potential of fault plane and of avoiding seals is also key in all of this. And then through time, of course, as deformation continues, the formation condition continues, changes through time. The fluid properties, because of temperature rise, because of changes in the heating component of that basin, they all have direct impacts on whether we'll find a working system or not. So we can apply, so this is the last bullet point I have. We can apply these concepts in de-risking new plays in frontier exploration location, as well as better understand existing prospects in mature development assets.